You know, after all the hassle of getting this equation of nitroglycerin and the decomposition it undergoes balanced and all, I decided to leave it up there and talk about another part of chapter 4 that is also wrapped up in this equation, and that is, this is an oxidation-reduction reaction. It's an electron transfer. And so we're going to take this thing and assign oxidation numbers and look at what part of it is oxidized, what part of it is reduced. And after all, it gives us a chance to talk a little bit more about nitroglycerin, the explosive compound that goes into dynamite. And nitroglycerin, you know, let's face it, this is kind of a fun molecule. You give it too much of a shake, it go boom. And, you know, that's kind of makes it an impressive one. We are actually going to need to look at the Lewis structure of this thing in a few moments to fully understand it. But we're going to do it, assign the oxidation numbers and then look at the oxidation and reduction processes that go on in here and even count up the electrons. So away we go. A quick reminder of assigning oxidation numbers, treating atoms in these types of compounds, whether it's ionic or in this case covalent compounds, as if they were ions. And there's a lot of different rules for assigning oxidation numbers, but there are only 3 of them we're going to need here that are really important. And I'm going to begin actually over here with the simpler molecules and work my way back to the nitroglycerin. And the most important rule at the start of this process is going to be, remember, the oxidation number of all elements in their natural state is 0. That doesn't mean oxygen atoms or nitrogen atoms. It means N2 molecules, the way we find nitrogen in the atmosphere, and O2 molecules, the way we find oxygen in the atmosphere. So I'm going to make a line down here, and let's just label it oxidation numbers. And they are going to be 0 for O2, 0 for N2. So far, so good. Now we have a chemical compound here. A critical oxidation number rule to remember involves oxygen. It always has the oxidation number -2 unless it's elemental oxygen, O2, or if it's combined with fluorine, not the case here, or if it's in a peroxide, which is not the case here either. And so very common, -2. I'm going to write that up there. The other one that's really important is hydrogen, and this is a pretty straightforward one. Hydrogen always has a +1 oxidation number when it's combined with nonmetals like these, -1 oxidation number when it's combined with metals. Not the case here. So far so good. Another oxygen here in carbon dioxide. I use the oxygen rule, -2. Now, I'm going to figure out the oxidation number of the carbon. Some of you could look at it and go, it's +4. I'm going to show you the process of coming up with that. Because carbon, like other elements that sit there kind of in the middle of the periodic table, they do not have easily assigned oxidation numbers. They can vary quite a bit. So this one you really do have to kind of figure out. And the way you figure it out is the following. You look at carbon dioxide and remember, for a neutral molecule, the oxidation numbers of carbon and oxygen have to add up to 0. It's a neutral molecule. Now, the oxidation number of the oxygen itself is -2. And in carbon dioxide, there are 2 of them. So there's the oxidation number, and there's the number of oxygens. And that has to add up with the oxidation number of the carbon, I'm going to leave that blank for a moment, times the number of carbons. Now it's only 1, so I'm going to just write a 1 up there, but for completeness, I'm going to include that 1 just because other examples you might not have a nice, you might need to include a number other than 1. But the question now is just simply, what number makes this equation possible? Makes it true. And of course, clearly it's got to be a +4. So that one gets written in over here. Now, the oxidation numbers of the nitroglycerin itself. And this one is going to be tough because it's a complicated molecule, but there's 2 of them that I think we can assign pretty easily. Oxygen, because it's always -2, except for those unusual cases, one of them being molecular oxygen. And hydrogen, always +1 when it's combined with nonmetals, as it is here. Carbon, left to be determined, because carbon usually has to be determined. And the nitrogen, another element closer to the middle of the periodic table than oxygen is, and that one can have quite a wide range of possible oxidation numbers, as it will, as this one does here. Now, to determine these oxidation numbers, I am going to invoke a little bit of deeper chemistry knowledge than the standard problem here might give, because this one, it brings up a lot of nice issues, and that is the Lewis structure of nitroglycerin. And the Lewis structure of this molecule is a fairly straightforward one. It has the 3 carbons like this. And then it's these nitrogen groups, and I'm simply going to write them in as NO3s. I'm not going to give the full details of how they're bonded, because there is some, Gen Chem 1 stuff in there about, double bonds and resonance structures and all that fuss. And I'm just going to leave it in there here, except to point out they're in there as nitrates, NO3 minus. Now, that's critically important for why this is such an interesting molecule, but for our purposes, that's how all of these nitrogens and oxygens of the nitroglycerin are sitting. They're all in there as nitrates. So what I need to do is determine the oxidation number of the nitrogen in nitrate. Now, the oxidation number of the oxygen, still -2, but this is an ion. The oxidation numbers here have to add up not to 0 like they did for a neutral molecule, but to the overall charge. Here, -1. I'm going to do exactly what I did before. The oxidation number of the oxygen, -2. There are 3 of them. And the oxidation number of the nitrogen, not known yet. And yes, there is only 1 nitrogen, but I'm going to go ahead and include the 1 as well. And so the question is, just like the previous case, what number goes into that slot to make this equation work? And of course, it looks like it's going to be a +5. 5 minus 6 is -1. So positive, I'm going to go ahead and write the positive sign in there. +5. Now, once that's determined, then we can figure out the oxidation numbers of the carbon. And these are not going to be totally straightforward. I'm going to cheat on these just a little bit. But in order to determine these, I need to kind of come up with the overall charge on each component in here. What I've got here are the oxidation numbers of these 3 atoms. But in order to get this one, I'm going to need to take into account the fact that each oxygen nitroglycerin has a -2 oxidation number. There are 9 oxygens in there. There's a total of -18 negative charges or negative oxidation numbers associated with the oxygens. Same thing here. There are 5, +5 is the oxidation number of nitrogen. There are 3 per nitroglycerin molecule, +15 associated with the nitrogens, 5 hydrogens +1, +5. Notice what that comes out to: 20 positives, 18 negatives. This is a neutral molecule, so the oxidation number of the carbons, I'm going to leave that one blank, plus the oxidation number of the hydrogens times the number, plus the oxidation number of the nitrogens times their number, plus the oxidation number of the oxygens times their number. Okay, all of that, -18, +15, +5, that comes out to be +2. There are 3 carbons in here. And so what I'm going to do is, you're going to come out with a fraction. If you do it just strictly algebraically here, it's going to be a -2/3 to make that work. But I'm going to cheat it a little bit with 3 different carbons in here. I'm going to call it -1, -1, 0. I'm going to give, the carbons are slightly different. These 2 on the ends have 2 hydrogens attached. This one has only 1 I'm going to assign them oxidation numbers -1, and 0. So to avoid this kind of fraction business that seems to fall out of this quick little calculation here. Okay, and so when I put in that -2/3, then yes, indeed, all the oxidation numbers add to 0 for this neutral molecule, just like they ought to. So there's all my oxidation numbers, including doing a little trick here to make it all work out right. But now that I have my oxidation numbers in place, I can now look at how does all of this stuff change. And one of the most startling changes that occurs is the nitrogens, +5 to 0. Every nitrogen here does that. Okay, so I'm going to mark that one. Nitrogens, +5 to 0. That is most certainly a gain of electrons. And in fact, this is what we call a reduction. I know. So the worst terminology in all of science is gain of electrons is reduction. Just get used to it. That's what we call it. Okay? And so nitrogen here is being reduced, and we're going to count the number of electrons involved in that process in a few moments. But if there's a reduction in this type of reaction, there must be an oxidation to go with it. And here it is. It's on the carbons. Just look carefully at what happens here. The carbons, -1, 0, all of them to +4, okay? These are all losing electrons, loss of electrons. This is what we call oxidation. Okay? Yeah, I know, I'm overlapping here, but who cares? Okay, oxidation. The carbons are being oxidized, the nitrogens are being reduced. Now, a few of you might spot there is actually another one in here, a little bit of a surprising change. The oxygens. 2 out of all the different oxygens in here, 2 of them are actually also losing electrons and being oxidized. I'm going to kind of do it that way. Okay, so there is another oxidation loss of electrons, -2 to 0. Okay, another oxidation going on. Okay, now what we're going to do now is just take a look at the actual number of electrons being involved here. And in a properly balanced chemical equation, which we dearly hope this is, the number of electrons being lost and the number of electrons being gained must be the same. So I am going to make myself a little more room here. I'm going to take this Lewis structure part out, and we're going to count a few electrons. So be with you in just a moment. Well, that was fun. Now, I want to look at the actual number of electrons involved here, okay, because there's quite a bit going on. Now, looking at the nitrogens, if I take the entire balanced chemical equation in here, there are 4 molecules of nitroglycerin, 3 nitrogens each. There are a total of 12 nitrogens, and it works out the same over there because we've already balanced this thing. So 12 nitrogens are gaining 5 electrons each. Do you realize that is 12 nitrogens gaining 5 electrons? That's 60 electrons, okay? 60 electrons gained by nitrogen total, okay? Now I want to look at the other side, okay? That is the reduction part here, a total of 60 electrons overall. Now I want to look at the oxidation part. We have over here in the nitroglycerin 4 times 3, 12 carbons. Okay, now there are 12 carbons total, but with this split here in the oxidation numbers, what I want us to get at is out of each and every nitroglycerin, 2 out of the 3 are moving from -1 all the way to +4. So if 2 out of the 3 per molecule, 4 molecules total, 8 of these electrons, 8 carbons are losing, okay, -1 to 4, 5 electrons each, Okay? And that means 40 electrons lost by those carbons. The remaining 4 carbons here, okay, 1 per nitroglycerin molecule, 4 nitroglycerin molecules total. 4 of these carbons are losing 0 to plus 4, okay, 4 electrons each. And that would imply then 16 electrons lost by the other carbons, okay? 40, 56 electrons being lost, 60 electrons being gained. We are almost going to feel a sense of panic like we did when we did the balancing of this thing and found the oxygens initially didn't work out, but then we go, the oxygens. There is actually another oxidation process going on. Of all 9 times 4, of all 36 oxygens in the nitroglycerin, all of them end up in either CO2 or water, except 2. The ones in CO2 and water, -2, -2, negative, don't change. So they aren't involved in the electron transfer. But 2 of the oxygens are, okay? So overall, only 2 oxygens, okay? So only 2 oxygens, okay? But they are losing -2 to 0, okay? 2 oxygens losing 2 electrons each. And what does that add up to? Oh, yes, indeed. 4 electrons lost by the oxygens there. And there it is, 40 plus 16 plus 4, 60 electrons lost by carbons and 2 of the oxygens, okay? They balance. A properly balanced chemical equation should balance in the number of atoms. It also will balance, if it's a redox reaction, in the number of electrons lost and the number of electrons gained. Final thing to say about this. Nitroglycerin, dynamite, boom, explosions. It's a well-known molecule. It has the property of being an explosive. I want to mention briefly why this one is explosive, while something else that we know gives off a lot of energy when it reacts, something like gasoline when it combusts, burning gasoline, is also a very energetic reaction, but it doesn't explode, okay? At least not conventionally it doesn't. So imagine this for a moment. You have, let's say, a gallon of gasoline, and you put it in a container, a bucket or something, and you throw a match on it. Sure enough, it's going to burn. It's going to burn hot. If there's combustible stuff around, it's going to cause a bad fire. You know, not recommended to do that sort of thing. But I want you to realize something. For that reaction, you know, gasoline, octane, C8H18, is the reducing agent plus O2 from the atmosphere is the oxidizing agent. Of all those molecules in that gallon of gasoline, when you throw the match on it, do you realize only the molecules at the surface are actually in contact with their oxidizing agent, the air and the oxygen that it contains? So the vast number of molecules in that bucket of gasoline are not going to react. They're not in contact with the oxidizing agent. Oh, sure, the top layer is going to burn off, go off as CO2 and water vapor, and the next layer will be exposed and it will burn as well. And so the whole thing will burn and it will give off a lot of energy, but it won't do it immediately and it won't do it explosively. Octane is a fuel that we combust for energy. Nitroglycerin, on the other hand, realize this molecule has both the reducing agent, the part that gets oxidized, the hydrocarbon component, the C3H5, and the oxidizing agent, the part that gets reduced, built in. There's no, oh, only these at the surface can react. Every single darn one of these molecules can react immediately. And that's why this reaction is so much faster and explosive, whereas a reaction like the combustion of gasoline, while very energetic, is not an explosive reaction, at least not the conventional way that we do that reaction. There's a lot of chemistry 1146 stuff here, the chapter 4 stuff in balancing and the redox, assigning oxidation numbers and recognizing the redox reaction. In chapter 5, we were going to look at the energy of this reaction, actually put a number on how much energy comes out of this type of reaction. In chapter 14, that's where we talk about speed of reactions and how greater amount of surface area can really change the rate at which a reaction occurs. And even all the way back in chapter 19, near the end of the course, we will look at the fact that nitroglycerin is a liquid. These are all gases. That actually plays a fairly big role in determining just how energetic this particular reaction actually is. So there's a pretty deep redox problem, for a chapter 4 level kind of stuff. So if you can grasp how this one works, you can handle just about anything we're going to see in class. So look it over and feel free to ask questions about it if you need to, and talk to you later.